Hello and welcome to the Unit 1 podcast. Today we're going to be discussing section 4.2. I'm Mr. Sakaguchi,
I'm Mr. Lin.
and today we're going to be discussing subatomic particles and how it relates to the modern model of the atom. Here we go. The first component of the atom to be discovered, or first building block, was the electron. And the idea of the electron first came about through electricity itself. They were looking to relate matter and nuclear charge. And at this time, electricity was kind of a new phenomenon. And through the study of electricity, they developed something known as a cathode ray tube.
Now, a cathode ray tube is essentially an evacuated glass cylinder with a positive and a negative side.
One end is known as the cathode, that's the negatively charged end, and the anode is the positively charged end. William Crookes was the fellow who actually designed the cathode ray tube, and what he did is he took the tube, pulled out all of the air out of the tube, and then it would inject in pure elemental gas. And what he noticed is that he would see this ray traveling from the cathode to the anode, which he called a cathode ray. It was a charged particle because it bended in response to magnetic and electric fields. It had a negative charge based upon how it behaved to these fields.
It was also found with no matter what kind of gas that he put in there, all of them responded similarly. So that means that all matter probably had electrons, or sorry, this electromagnetic effect at this point.
And the other thing about cathode ray tubes that you might not realize is that this is like the grandfather that led to the invention of televisions and computer monitors. Basically, those were modified cathode ray tubes, which we don't actually use anymore, but that led to the beginning of that. A protege of Crookes was J.J. Thomson, and basically he took the Crookes tube, or cathode ray tube, and studied the electron a little bit more carefully. He was able to actually determine the charge to mass ratio of electrons. Basically, the way he did that is he measured the cathode ray tube, the cathode rays in response to different magnetic and electric fields, and basically he was able to show that the mass of the electron was much less relative to a hydrogen atom.
Now, this was an important discovery because originally everyone thought that atoms were these really small marbles, okay, according to Dalton's theory for atoms. But since Thomson came up with the idea that there's an even smaller part of an atom, this opened up a whole new series of observations and experiments to find out what was next. Because if you found one small particle that explained the atom, there had to be other small parts. And this is important because it leads to understanding how it all works together and how to get them to react.
Yeah, at this time they had a lot of indirect evidence, right? For instance, they knew atoms were electrically neutral, but they had this negative component. So there had to be something to balance that out. Also, a lot of the mass was missing because of the small mass of the electron. So there had to be other components that had to make up the missing difference in mass. Millikan was able to kind of further the work of Thomson. Basically, if you have the ratio, if you can determine either the charge or the mass, you can figure out both the charge and the mass of an electron. Robert Millikan did what is known as the famous oil experiment. So what he did is he basically sprayed mineral oil into a very, very fine mist, such a fine mist that was able to actually pick up electrons or static electricity. And then as this atomized oil fell, he was able to expose it to electric field and make measurements on the forces acting upon the oil. And basically he was able to use that information to calculate the charge of electrons.
Which turned out to be really, really small. As you can see on the screen, it's 1.602 blah, 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 times 10 to the negative 19 coulombs. That's a really small number, but since it gets used so often in the chemistry course, It's referred to simply as just a -1, and that -1 is just symbolic of that really small charge.
Yeah, so coulombs is the actual measure of charge, and we don't really use that precise of a number in chemistry. We just call it a -1. And notice again exactly how much smaller the mass of the electron is compared to a hydrogen atom. Again, unbelievably small, and again, evidence that there are other components present.
There had to be more out there.
Yeah. Okay. Through these results, Thomson was able to kind of modify the Dalton model of the atom, and he came up with what is known as the plum pudding model. Plum pudding was very popular back then. We call it, in probably modern times, be easier to understand, as the chocolate chip cookie dough model. The idea here is that the cookie dough represents the uniform positive charge, and that the electrons are like the chocolate chips, kind of randomly spread throughout.
Now, the reason it was set up this way is because they knew that electrons existed, so hence the the red dots, the yellow dots, but they didn't know anything about the positive charge, so they made it sort of a blob, a field, just a globity gook of stuff that the electrons would float inside.
Thomson's protege, Ernest Rutherford, basically tested the Thomson model, and he came up with this experiment, which is summarized here in the figure on the left. This is known as the gold foil experiment. The idea here is that he took gold and he pounded it into a very thin layer, which was only a few hundred atoms thick, and he put it in the center of this massive display. And what he was going to do is he was going to shoot alpha particles at the gold foil, and then alpha particles are radioactive, and then he had these detection plates that would detect the path of the radioactive alpha particles. So wherever the beam landed, these plates would pick it up. Now if we go back and look at the Thomson model, remember there's a lot of open space inside of this atom, and the gold atoms relative to the alpha particles are much, much larger. So the idea is that there's a lot of massive open space in the gold atoms, and these tiny small alpha particles should be able to go right through, according to the Thomson model.
Now, this didn't actually work out as Rutherford and Thomson's model predicted. What wound up happening was that the alpha particles flew through the gold foil, and most of it did hit on the other side, but they also wound up with some other results that they weren't expecting, shown here, where scattering of the alpha particles bounced off of something and ricocheted back in all sorts of directions. Now this is kind of strange. It'd be like saying you're going to fire a cannonball through a piece of tissue, and instead of it flying straight through, it bounces right back at you. It's not what you're expecting. Rutherford wasn't expecting this, so this caused him to think about a new model for the atom.
So while the majority of the gold atom is actually open space, these alpha particles had to be hitting something larger than itself, and something that had to be dense, large, and of like charge to cause these ricochets. And based upon these ideas, he came up with the concept of the nucleus, which changed the atomic model from Thomson to Rutherford. The idea here is that the atom is still mostly empty space. This is something that's still in common with the older Thomson model, in that these electrons occupy the empty space, but the positive nucleus, which is the dense core in the center, holds the electrons.
And as you can see in the model here, where you have the positive core in the center, this was because the alpha particles are positively charged, and like charges repel each other. So if the alpha particle flew in and hit the nucleus, positive nucleus, that was what was causing the bouncing,
so in other words,
bouncing back.
It would ricochet as opposed to sticking to the nucleus.
Or flying straight through if it was just a lightly dense positive field.
Yeah. And it also kind of explains the whole idea that atoms are neutral. So now we have something that's positive to counteract the negative charge of the electrons. Now protons were later discovered through a modified cathode ray tube experiment. Basically, they found that there were beams going in the opposite direction of the cathode rays. known as canal rays, and they were able to identify these as protons. Later on, once they had identified the proton and quantified its mass, there was still a mass difference between protons and electrons versus the actual masses of elements. So through other work, they were able to eventually figure out that there's a third building block present known as the neutron, which has a mass of a proton but no charge.
Now, you'll also notice that the proton is positively charged down here in the chart, in the notes, and also in the chart here. So now we have a layout of the positive charge of the protons, the negative charge of the electrons, and then the neutrons having that mass but no charge at all.
And then where they're found in the atom itself.
Right.
And this is it, and we're going to continue in the next section soon. And until next time.